Okay, we are rolling with the recording, I believe. Okay, so introduction to thermo. Nope, it's not writing.
The screen's on as well.
Yeah, okay, there we go. Okay, so intro to thermo. If we break down all of the complexity of the universe, right, thermodynamics basically breaks down into everything can be described by three variables. That is U, which is internal energy, S, which is entropy, and V, or density, if I draw a bar under it, like the specific volume, which is the reciprocal of that, is basically real space, so real 3D space. All of classical thermo is derived based on this assumption that there are only three variables of the universe. And what the goal of thermodynamics is to relate between these three variables. So essentially, we want to know what is U as a function of S and V, or what is S as a function of U and V, and so on and so forth. That's really the ultimate goal of what we're trying to accomplish here. So from these variables, we can break thermo down into a few tenets. We have the first law, which is essentially just energy conservation. We have the change in internal energy is equal to the amount of heat put into the system plus the amount of work put into the system. Now we break down the difference here between the D and the delta there to indicate that the D is an actual differential, which means we can integrate it, whereas the delta means we have to select a specific path, right? U is what they call a state function, so no matter which way we run the system, going from one starting U to another U, it doesn't matter the path. It's a state function. But Q and W, right, heat and work, they do depend on the path that you take, so that's why we write a little bit different notation. But we won't spend too much time on that in this class. The second law is arguably way more important and way more robust to thermo than the first law is, but it's always skipped over or just glossed over very significantly. The second law is written very simply as ds is greater than or equal to 0. Now I think next lecture we'll talk about how we actually take this ds is greater than or equal to 0 concept and apply it in sort of what we're used to seeing in terms of entropy balance. So there's a couple of other properties of entropy that are important to go over. Namely, the curvature of entropy. D squared S is less than 0. Now this means it is concave. So entropy as a function of any variable x always looks like this, no matter what. It's always concave. And this has to go to the absolute stability of the universe. So at equilibrium, right, this could be thermal equilibrium, mechanical equilibrium, chemical equilibrium, all forms of equilibrium, ds is equal to 0, and d squared s is less than 0, which means that entropy is equal to a maximum at equilibrium. So let's say, for example, we were to think of the opposite situation. If entropy was convex, that would mean it would look something like this. Now, if entropy ds equals 0 at equilibrium, that would mean it would sit right there. Now, that's a point of critical stability. So any small perturbation one way or the other would send the system into a state with a higher entropy. So you actually need this convexity, if that's the word, for the universe to be stable. Now, from the curvature of d squared s being less than 0, we get a number of other potential and important relationships that we'll derive later on in the class. But that means C sub v has to be greater than 0. Right? The heat capacity always has to be positive. When you put energy into a system, its temperature always goes up, and vice versa. Right? You can't have a negative heat capacity material because it violates the second law of thermodynamics. In addition, temperature has to be greater than 0. These all come from the stability criteria of entropy and its curvature. And in addition, dP dV at constant T is always less than 0. Now this is an isotherm, right? A deep P curve, like the ideal gas law, kind of has a curvature that looks like a radical function, right? That all comes down to the stability criteria of entropy. Okay. Now, one other thing that I really like is, where does the Gibbs phase rule come from? Well, if we only have 3 variables of the universe, U, S, and V, right? Then if we know any 2 of those, we should be able to calculate the third. That is the foundation of thermo, and that's what it's trying to accomplish. So in that case, again, if we want U, we should be able to derive a function of S and V. If we want S, we should be able to derive a function of U and V. And if we want V, we should be able to derive a function of U and S. That is basically the Gibbs phase rule. If we know any 2 of those variables, we can calculate the third because it's a fully specified system. I can't independently vary all 3 of them. Otherwise, that means that there's some other property of the universe that we're missing out on. So the basis of the Gibbs phase rule comes from the fact that you have to distill down thermodynamics to being only a function of 3 variables. But we don't use just those 3 variables. In fact, we hardly ever use those 3 variables when we do modern chemical engineering thermodynamics. Most of the time, we're doing enthalpy as a function of temperature and pressure. So if we look at derived variables, temperature is defined, right? Temperature is a defined quantity as ds du at constant v. So it is the slope of a plot of S versus U. That is what temperature is defined as in classical thermodynamics. Pressure, negative P. Sure.
1 over temperature, or the inverse of temperature?
Yes, the inverse of temperature is defined as ds du at constant v. And oftentimes when we talk about stat mech, 1 over temperature is a much easier unit to work with than temperature itself. So you have this variable called beta, which is equal to 1 over kBT. That's a commonly used variable in statistical mechanics. So again, but with thermo math, it's very convenient. We could just rearrange these expressions any way we wanted to. So if you wanted to take the reciprocal of this expression here, you could just do that, and you can get temperatures equal to du ds at constant v. That's why thermo math is a lot more fun. You don't have, it's not as stressful as like math. Pressure is defined as du. Actually, these are all specific quantities here. dV at constant S. Right, so pressure is how does the energy change when I compress or expand a system. So we have a few more derived units that are very commonly used as well. H is defined as U plus PV. Now these are just convenience functions. So anytime you calculate the Gibbs or the enthalpy or the fugacity, what you have to remember is these are just convenient functions for you to calculate that people have found they just pop up in equations a lot. So they're nothing more than a mathematical simplification. So this is used often in open systems. So that's why we care about enthalpy. It's very useful in open systems. We have A, which is defined as U minus Ts, and G, which is the Gibbs free energy, is H minus Ts. And these are good for phase equilibrium. So the thing to remember with thermo is that it's just sort of like, it's just stacked on top of each other. So if it seems totally arbitrary, that's because it is. This is just a construct that people have found becomes very useful to perform calculations. Could you do thermo in a different way? I'm sure you absolutely could. But what we're teaching here is we're not teaching basically the answer to all questions in the universe. What we're teaching in a thermo class is the system that people have used to store, tabulate data, and for you to unpack it and use it for Rankine cycle calculations or phase equilibrium calculations. What we're doing in classical thermo is we're condensing the complexity of the universe to as few of variables and as few of measurements as humanly possible. So that's what we're doing. And I feel like a lot of the times in sort of an undergraduate class, the emphasis is getting you guys to the finish line to actually do, an XY diagram on a distillation column, then spending actually a little bit about the history of it. So I think that mostly covers the introduction that I wanted to go to before we go into the history of thermodynamics, right? So back in the day when thermo was first developed, they didn't know what an atom was. All that they knew was that they could burn coal and it heated stuff up, and basically people wanted to optimize steam engines. And so they came up with relationships between different properties. But they didn't know the underlying mechanism of how those properties were stored, right? So their goal was to figure out, how do I make measurements and how do I store information? And so what they found was that they wanted to relate between things like U, S, V, T, and P through equations of state, which relate between T, V, and P, right? Like the ideal gas law is an equation of state, van der Waals equation is an equation of state, Peng-Robinson, and so on and so forth, and material properties. For example, C sub V, C sub P, isothermal compressibility, and so on and so forth, right? Kappa T is the isothermal compressibility. Right? How much does the volume change if I increase the pressure is effectively what kappa T is here. So after classical thermo was already fully developed, that's when atomic theory started to become popular. So statistical mechanics is the challenge to relate between what people had already known about the relationship between all of these properties here to how does an atom influence that? Right? How are the properties of helium different than oxygen, different than methane, different than ethane, different than water? Right? What are the property differences of water versus ethane? And how does that impact what's going on in the system? Right? How do you scale up the concept that there's 10 to the 23 atoms in a mole? That's what StatMech's job is. So what we're going to do is we're going to go through the classical perspective and go through a little bit of the history of classical thermodynamics right now, but the entire class up until we start talking about StatMech, you really have to divorce yourself from what you already know. Right? In undergrad thermo, they say, oh, well, the heat capacity, that's the vibrations of the molecule, that's the rotations of the molecule, that's its translational velocity of the molecule. Right? But you have to remember that all of the nomenclature and all of the equations and all the math that we're doing was developed before anyone knew that concept existed. So thermo makes a lot more sense if you think about it in the abstract where you're saying, okay, internal energy, what is that really? Right? Is it just a magic force that holds energy? Yes. Right? So back in the day, internal energy is just magic energy. It goes into the system holds it somehow, and later on you kick it back out and you use it. Right? That is the sort of the mindset of what was going on back in the day. So keep that in mind. So whenever things seem to get arbitrarily complex and stacked, we talk about fugacity, which is a shift in Gibbs, which is a unit that's derived from combining T, U and S or whatever. Everything's just built on top. Just remember, they didn't know what an atom was. Right? This is the best system that they came up with, and it works really well, but it's somewhat weird in language, and it doesn't really fit in well with our current understanding. Okay. So let's go through a little bit of history to sort of convince ourselves of what the state of current state of the art was back when we're talking about classical thermodynamics. So what we're learning about now is sort of what people sort of understood back in the 1850s to 1900s. Right? That's kind of the era that we're at in this class for the first little bit. Okay, so back in 1774, we had an individual called Anton Lavoisier. A French, I don't know what you want to call it, philosopher, physicist, chemist. They all kind of blurred together back at that point. Anton Lavoisier is actually in my academic family tree. So if you go from like PhD to PhD to PhD, all the way back to 1774, Lavoisier trained one of my very early forebearers. So what he did is he burned diamond in pure oxygen. Right, so we still had an idea what elements were back at that stage, but we didn't know what the structure of the elements were or anything like that. Right, so we knew oxygen was oxygen, but we didn't know if it was like a ether or if it was continuous or if it was individual particles. In fact, most people did not think it was individual particles. Most people thought it was a continuous fluid that was indivisible, and you could keep slicing it and keep slicing it and keep slicing it. Sorry, continuously divisible is what I mean. So he burned diamond in pure oxygen and found that the mass was the same. So Lavoisier, if you guys remember, sort of came up with the law of conservation of mass. So in our language, we would write that dm dt is equal to the summation of mass in minus the summation of mass out. Now this would be something we would see in a mass balance in a chemical engineering process, whether it's a reactor or a distillation column or a separator or crystallizer, whatever the case is. So if you had a closed system, we had no streams in and no streams out. So this is for open. And if you had a closed system, dm dt is just equal to 0. Right? The mass cannot be changing in a closed system as a function of time. So we're going to ignore any sort of nuclear processes, and in fact, we're going to ignore any sort of quantum mechanics or anything like that as well. So everything we're going to be doing is all classical, no nuclear processes, no nothing. Okay. So I don't think anyone's going to have any issues with conservation of mass. So now if we go to conservation of energy, this is where we start to talk about the development of the first law of thermodynamics, which is all the first law of thermodynamics is just the law of conservation of energy. And in the case of what we commonly write it as du is equal to dq plus dw, we're mostly concerned with how much heat are we putting in and how much work are we getting out. Again, take that mental approach of we're talking about steam engines. Right? I want to learn how can I burn less coal and get a more fast ship. Right? So the military cared about it, industrials care about it, manufacturing people cared about it. Right? That was really the main emphasis back then of study, is you want to maximize your work output. I want to burn as less coal as possible, or trees, or whatever you were burning back then, and get the most work out. So there are other forms of energy, and there's kinetic energy, potential energy, electrical energy. So if this were a different type of thermo, we would spend maybe a little bit more time talking about that. But in general, the amount of energy stored in chemical bonds is way, way, way more than gravitational potential energy or kinetic energy. So we typically just completely forget about those because the mass, so the energy stored in chemical bonds is huge. So for chemical engineers, that's mostly what we care about. Okay, so conservation of energy. started basically back in 1638. Now, of course, there's a lot of Greek philosophers and Roman philosophers and things like that who had all postulated about these sort of conservation laws. But we're going to focus more on when sort of the rubber hit the road and things were getting formalized with the scientific method. We had Galileo. And he did pendulum experiments. So he took a very large mass and put it on a pendulum and had it swing back and forth. Now, he originally tried these experiments with a ball sort of on a ramp, but he found that there was too much friction and the ball would slow down over time. So ultimately what he decided on was a big weight on a string and watched it swing across. And if you look at the energy as a function of time, it's the total energy here is the same, but it transitions between gravitational potential energy and kinetic energy based on how it swings. And I believe it's sinusoidal, so it should look something like this. So this would be the potential energy here. Right, this would be at the top of the swing, so it would be like this. And it would swing down. And then the kinetic energy would swing up. So basically what Galileo had demonstrated is that you would convert between two forms of energy and you would keep the total the total energy of the system constant. Okay, but the question is, how does this relate back to heat? Right? This is just transitioning between potential energy and kinetic energy. In this case, this is gravitational potential energy. So, in order to help address the question of what is heat, what is work, and then how are the two interchanged, there were other theories that were in existence before the first law of thermodynamics came to the foundation. Specifically, we're going to talk a little bit about a theory called caloric theory. So this is, of course, a now disproven theory. Caloric theory. Okay, I promise I will try to improve my handwriting on this device as time goes on. Okay, so this is about the mid-1800s when this was actually the dominant theory in thermodynamics and science. So the idea was that caloric was a weightless gas. So they thought it was conserved and it carried heat. Right, because we already had the law of conservation of energy. We already had the law of conservation of mass. And they thought that heat was just sort of its own different type of energy, that you could transition from something that was hot to something that was cold. But the issue was that it was wrong. It's the number one thing. So what people thought cold is that a cold object didn't have caloric in it, but a hot object had lots of caloric in it. And so this may seem like crazy, totally debunk, but Carnot actually used caloric theory to derive the Carnot engine. So there was still some usefulness to the theory. It wasn't just total, kind of crackpot type thing. So Carnot used it to develop the Carnot cycle, and it went on for quite some time, actually, until Joule went on and sort of solidly disproved it. So, but that doesn't mean that people were 100% with it. There was a particular set of experiments done in 1798 by an individual named Count Rumford. And I believe, okay, yeah, so this is Munich, Germany, but I think back then it might have been the Prussian Empire. But anyway, so Count Rumford worked at a factory that made cannons. And what he did in his experiments is he had a tank of water and a cannon. And in order to make the cannon, they had a borer that spun around. So what they found in sort of his documentation of making cannons is that water boiled in about 2.5 hours. But what he found interesting, this gentleman, Count Rumford, was that he could continue to boil water indefinitely. So no matter how long he bored out this cannon, right, he could always continuously boil water, meaning that they were always continually transferring caloric into the water. And so his conclusion was basically that, no, caloric theory is wrong. It cannot be a conserved quantity because I can create as much of it as I want to as long as I bore this cannon out. Right? So they were converting basically the mechanical energy through friction to heat energy as the way that we would normally think about it. But the problem was that these experiments, as you can tell, are not the most precise experiments. This is a big industrial operation, a big vat, and they're spinning down basically a mechanical borer into some metal and measuring the time it takes to boil water. So they weren't accurate enough for most people to really sort of sign up and discount caloric theory because it was a useful theory and it had been used to derive concepts. So, okay, time-wise, what ended up happening next was that then Joule, James Prescott Joule, in the 1840s, did some more precise experiments. So what Joule ended up doing is he used viscous heat dissipation. He would force water through narrow capillary channels and cause heating to occur in that way. And he was able to do much more accurate measurements to demonstrate that, yes, you could continuously generate heat. In addition, Joule he converted electrical energy directly into heat as well. So what Joule really demonstrated is that you could translate between different forms of energy and convert from heat to sort of internal energy and back and forth, and it didn't matter what the source of energy was. The viscous dissipation was directly converting mechanical energy to heat in the form of viscous dissipation. He took electrical energy and directly converted it to heat. And so that was really the foundation of the first law of thermodynamics, showing that you could directly relate between electrical, mechanical, and heat energy, and it was all the same. And all that mattered was the energy itself just being stored in different forms. So he did mechanical to heat. And this is by viscous dissipation. And electrical energy to heat by induction heating. But interestingly enough, I have a little side notes here. His publication was originally rejected by the Royal Society of London. So he had an uphill battle, sort of highlighting how entrenched the caloric theory was sort of at that time itself. Okay, so that basically brings us to the first law of thermodynamics. After Joule, we have the solid foundation for the first law. Now we'll talk about the second law next week. So what I want to do right now is go really quickly to parallel what we did in classical thermodynamic development to the development of modern atomic theory, just to give us a little bit more context of what the current state of the art was in the understanding of how matter stored energy. So again, we're gonna ignore, Greek philosophers who, first sort of said, oh, I bet there's some unit called an atom that's indivisible, and that's what everything is made out of. Right? So people had already had sort of these notions, but again, we're going to focus on when things really got real, and a lot of people started believing it more from a scientific perspective than just a philosophical perspective. So the founding father of modern atomic theory is an individual named John Dalton. And I believe If you think back to sort of general chemistry, there's a Dalton's law, something to do with the volume of gases or something like that. I honestly don't remember it too well. So he lived from 1766 to 1844. So he discovered that certain elements had the same ratios. So certain compounds had the same elements of ratios. So for example, water always had the same ratio of hydrogen to oxygen, right? In this case, it was typically more of a mass ratio than it was a molar ratio, because they didn't really know quite what the molar ratios were. But they knew that a lot of compounds, they always had exactly the same ratio. And so basically he deduced that matter must be constructed by some individual building block that is oriented in basically a repeating pattern, right? Because why else would they have exactly the same ratio? It wasn't deviating at all. It was very specific and reproducible ratio. So now where things really got important was with the work of Ludwig Boltzmann. So he was 1844 to 1906 is when he lived. He was an Austrian physicist, philosopher. It's all lumped together back then. The fields were much more overlapping. So his major contribution to atomic theory was the kinetic theory of gases. And this was developed in 1871. And this overlaps a little bit with kind of the stuff we'll be talking about with thermo, but we'll see in a minute why the 1871 date was sort of irrelevant. So no one believed him. So what the kinetic theory of gases does is basically it says, well, a gas consists of particles, and they have a particular velocity distribution, which means they have a particular energy distribution. So the Maxwell-Boltzmann distribution is named after this here. That's the velocity distribution of gases. So James Maxwell and Ludwig Boltzmann sort of both independently developed the kinetic theory of gases. So what he basically did then is the kinetic theory of gases, it estimated the energy of a single particle as a function of temperature. So this was the very first instance where someone was able to assign a specific meaning to what temperature actually is. And so the Boltzmann constant, Kb, which is what we still use, is 1.38 times 10 to the minus 23 joules per Kelvin. That is the amount of energy that is stored in the translational movement of a single particle as a function of its temperature. So R, the gas constant, right, is equal to Avogadro's number times by the Boltzmann constant. And that gives us units of 8.314 joules per mole Kelvin in SI units. The problem is no one believed him. They believed the accuracy of the predictions, because the whole point of development of the kinetic theory of gases was to predict the properties of fluids at high temperature and pressure, specifically steam. Right? Because if you were trying to improve the efficiency of a steam cycle, you wanted to be able to know, okay, let's say I ran my experiment at this temperature and this pressure. Instead of doing all those experiments, if you had a theory to predict the properties of water and you knew what you're trying to get out of it, you could save a lot of money. So he was able to very accurately predict the property of fluids at high temperatures and pressures, which no one else could do with this theory, but everyone just thought it was a mathematical construct. They said, okay, well, this number here, 10 to the minus 23 joules, that's way too small. No one's ever going to be able to see it. No one's ever going to be able to measure it. It's not worth your time even thinking about it as a real conceptual basis. So everyone's opinion on the matter was, great, it looks nice, but it's not actually real. It's just a mathematical approximation. And so ultimately, Boltzmann sort of took this a little bit too much to heart, and he ended up committing suicide in 1906. So that's how he met his demise. So to give you an idea about how entrenched the opposition was against the idea of an atom, That was in the period of the 1870s to the early 1900s. People really didn't like the idea of an atom. So the atom really got to be believed through Brownian motion. So a botanist, I forgot his first name, named Brown, in I think the 1840s, observed that if you had a small little piece of pollen, it would jump around in the fluid following a seemingly random path. So Einstein, in 1905, in his extremely prolific year, where he wrote about special relativity, the photoelectric effect, and Brownian motion, he derived and proved that the only way for a pollen particle to have been jumping around is if there were particles that were even smaller than it, causing it to move. So he worked out the math and showed that unless you have particles that are extremely small, you cannot get Brownian motion to occur. The particles should just stay exactly stationary. So what happened then is a French physicist named Jean Perrin in 1908 used Einstein's theory and Brownian motion to very accurately measure Avogadro's number, and through that, the Boltzmann constant. And basically proved Boltzmann theory correct.
So if he would have waited 2 years, he would have been fine?
Exactly.
Wow.
Well, he had other mental issues as well. But effectively, yes, if he had known about Einstein's paper, maybe things would have been a bit different. But anyway, so not until basically 1908 and 1905, between the combined efforts of Einstein and Perrin, did the idea of the atom really start to take serious hold across the scientific disciplines. So, and everything that we're going to cover in classical thermodynamics basically goes up into this point. Now, they extended it, and I'm trying to remember, I think Gibbs was in the 1840s as well. But basically, from 1908 onwards, that's really when things start to get real in terms of the development of quantum mechanics, the development of statistical mechanics. Now that we know an atom exists, we've already got this developed, established theory of thermodynamics. How do we reconcile those two together? And that's what StatMech is. So it introduces the concept of an atom. So throughout the class, at least the first half, you have to force yourself to remember, God, this seems really arbitrary, and it seems overly complex. Well, that's because it's the best system that they had, and as it turns out, it's really accurate. I've got a few more little snippets here among the history of atoms. In 1889, J.J. Thomson discovered the electron. He did this by using a cathode ray tube, which basically means you have really high voltage potential in a vacuum, and electrons will jump through the vacuum to sort of travel and alleviate that voltage potential. And he had a deflecting magnet, so he could find that there were charged particles. So that's how J.J. Thomson discovered the electron. And in 1911, one other quick comment. So in 1889, this is where they had the plum pudding model of the atom, where you had a big positive charge, and then they thought there was just a sea of electrons, right? So it was still a continuous sort of structure of matter down on the very, very small scale, right? But they thought it was just a continuous sea of positive charge with electrons floating around, because they only knew about that one subatomic particle, which is the electron. And then in 1911, Ernest Rutherford he discovered the nucleus and the proton. And they did this by shooting alpha particles through thin gold foil. And what they found is that a very small number of them would be reflected back. And they worked out the math that the nucleus was, several thousands times smaller than the atom itself. And so that most of what we see is empty space, right? The nucleus that contains almost all of the mass is really, really teeny. So basically what we have is we have the development of thermodynamics, ends around the 1850s. And the development of the atom really only begins in the 1870s. So there's a significant disparity in those two materials itself. Okay, so we don't have time to go all the way through what I wanted to cover. We're a couple pages behind. But basically we'll talk about that next week, or sorry, not weeks, on Friday. Basically taking all of what we learned so far and then just writing down what everyone has seen as sort of the traditional equations that we all assume are the first law and the second law, right? Summation of enthalpy in times the mass is equal to Q plus W and all that kind of stuff, right? But I think it's really useful to have context, especially with thermo, because it's such kind of an arbitrarily confusing class that I think it's really nice to sort of remember where we're actually coming from. Okay. And on Friday, we'll also do the same thing like we did today, but with the development of the second law of thermodynamics. Okay. Any questions so far? I'll have a homework posted very shortly, probably tomorrow at the latest Friday. I know you're all disappointed on that. So we'll have homework posted. It won't be like touchy-feely stuff like this. It'll be actual quantitative calculations. But anyway, yeah. Any questions?
Yeah, when will the homework, so it'll be posted on Canvas?
Yeah, I'll post everything to Canvas. And I'll probably do paper assignment hand-ins. In the past, last year when we had the class, when we had the video lectures, we had a distance learning course. We had everything electronic. But I think I'll go back to paper just so it's easier.
So the homework will be posted?
Yeah, I'll post it to Canvas tomorrow or Friday. And I'll send an email out when I send it out. And then it'll be due in like 2 weeks or so, or 10 days or something like that. You'll have enough time.
Do you have a particular days for the homework is due?
Usually like a Wednesday or Friday. I don't like to put them on a Monday because then that doesn't give everyone a chance to ask questions in class before. So it'll either be a Wednesday or a Friday usually. All right.
I'm still trying to get internet in my apartment.
Yeah. Okay, guys. Well, see you on Friday.